Water. In fact, you can see from the numbers, there were 224 molecules of water formed to every 54 molecules of biotite. I thought, hello, I've now got water. I'm going to predict that I'm going to find more polonium radiohalos at that spot in those metamorphosed sandstones than anywhere else, because I've got a source of polonium in the zircon crystals, I've got a repository in the biotite, and now I've got hot water. Okay. Question?
You say that this process is producing water. Could that have been part of where the water for the flood came from?
Not in this instance, no. So we collected a series of samples going right across, and you can see that it's almost perpendicular to those zones of different minerals in the metamorphosed sandstone. So that's a traverse. Now along that line we plot the number of radiohalos. What I do when I do this research, I do a procedure where I can get a statistical sample where I approximately 1,000 biotite flakes for every sample that I examine, so that I can compare sample with sample to quantify how many halos. This is the result. Right where this boundary, where this occurs, there's 4 to 5 times more polonium radiohalos than anywhere else in these metamorphosed sandstones, where you had much more water. So that was a prediction. Because of the hydrothermal hot water transport of this polonium, I predicted there would be more halos where there was more polonium radiohalos, where there was more hot water flow. Sure enough, slam dunk. Prediction fulfilled. In fact, interestingly, there's some metamorphic rocks in Norway, in the Bergen area. These are former magma rocks, we call them igneous rocks, that are similar to granites, that had been metamorphosed at depth inside the earth to a high grade, that is high temperature, high pressure metamorphic rock called a granulite, early in the flood, and subsequently during earth movements early in the flood in our time frame, hot waters had penetrated along fracture zones in this metamorphosed rock, transforming it into along the fracture zones, the hot water had transformed the surrounding metamorphic rock into a different metamorphic rock. And this different metamorphic rock, called eclogite, is not known to normally have biotite in it, and certainly with no biotite it doesn't have any polonium radiohalos in it. But interestingly, let me just skip through these. Some of these rocks actually do contain biotite in this instance. In other words, as the fluids went through and the rock cooled, the fluids actually also produce some biotite in these shear zones. Okay, and the interesting thing was, I don't need to go into these technical details, except the geologists, and this was written up in the conventional scientific literature, in using the radioisotope dating methods on these rocks in this shear zone, they demonstrated that the hot fluids had been travelling through these shear zones over short periods. Initially they estimated 18,000 years or less for this metamorphic transformation in these shear zones, but they dropped it down to less than 10 years. And that was radical. This was written up in Nature. But the interesting thing is, the biotite flakes contained polonium radiohalos from the hot fluids transporting polonium in. And that had fitted the short time scale, probably even shorter time scale. It would have been the biotite formed due to these fluid flows, which must have also transported the polonium. But of course the polonium-210, they were polonium-210 halos, only have a half-life of 138 days, and therefore rather than 10 years for this metamorphic transformation, it would be in less than a year. So that fits the flood timescale for this metamorphic transformation. So now we're seeing that the polonium radiohalos are actually helping us not only show that granites can form rapidly, but also that metamorphism of rocks has occurred rapidly. So I've continued this research, and I just want to quickly show this to you and then we'll finish. This is what I'm going to present also at the conference in Pittsburgh in a couple of weeks' time. In southeastern Australia, we have a classic metamorphic complex. It's a classic textbook example in the geological literature of zones of increasing metamorphism, that is the metamorphosis of original siltstones and shales into what we call schists and gneisses, which are metamorphic rocks. And at the very centre of this complex, the temperatures were so high that the rocks melted to form a granite. And you can actually literally walk from outcrops of fossiliferous sediments that obviously were formed during the flood across these zones of increasing metamorphism of the original fossiliferous sediments until you get right into the granite in the centre. So this is a geologic map, and the town of Cooma is at the centre of the complex where the granite is in pink, and as you go out, the metamorphic rocks get lesser and lesser from the heat and the intensity. Walking the other way from the white area out to the left, you've got fossiliferous sediments. As you walk in towards the granite, you get higher and higher temperature transformations of the original siltstones and shales. Now, I'd already found radiohalos in the granite, so I was interested to see there was a reference in the literature to uranium radiohalos in some of the surrounding highest grade metamorphic rocks. But the interesting thing is there was evidence of zircon crystals all the way through those metamorphic zones, and there were biotite flakes in all those metamorphic rocks. So I thought to myself, okay, I've got zircon crystals that has uranium and polonium, I've got biotite flakes, I ought to be able to find polonium radiohalos. Particularly where there was more water, you would have more polonium radiohalos. Here's some of the outcrops of these rocks from road cuts. That's what some of the rocks